Welcome, Collective Nation, to another installment of the Gen AI Collective podcast, Collective Intelligence. I'm your host, Thomas Joshi, ML researcher on the Stanford LLM project, Demonstrate, Search, and Predict project, former ML engineer, and our guest today is Professor James Zhu, Professor of Biomedical Data Science, and by courtesy of Computer Science and Electrical Engineering at Stanford University. Get ready to embark on an enlightening journey as we explore the world of AI and biomedical data science. We'll discover how AI and biomedical data science are revolutionizing healthcare with insights into emerging trends. We'll uncover how James is on a mission to democratize data through Stanford Data4Health Hub, and we'll navigate the challenges of achieving statistical rigor in healthcare-focused machine learning and how to do so in the real world. Pete will peer into the future as we just discuss untapped potentials in biomedical data science and AI. Get ready to be inspired. Let's dive in. Hi, James. Thank you so much for joining us today. We'd love to start us off by you just telling us more about your education, your prior work experiences, and how they led to your current work, just emphasizing why you made those past decisions for the audience.
Yeah, happy to. And thanks for having me here. I'm excited to participate. So I did my PhD, and my PhD work was primarily in machine learning and in applications for machine learning to medicine, to biology and medicine. So that was right around the time when deep learning type things were taking off, in the early, around 2010, 2011, that's where the deep learning was taking off. And I was always really interested in this intersection, of AI and machine learning, and looking at impactful applications of these algorithms, see how can we use them to improve human outcomes, improve people's health, improve society. So that's why this intersection of AI and medicine and healthcare is sort of what I was really interested in during my PhD. So I finished my PhD, it was at Harvard, and then I spent 2 years actually at Microsoft Research in the Cambridge, Massachusetts lab. And that was actually a really great place. It was a very academic environment. I was still doing a lot of work on AI and machine learning, and also medical applications. And that's where we actually started to do a lot of these works, looking at biases in algorithms. So we started this paper with a couple of colleagues at Microsoft Research looking at word embeddings. Now it's quite well known, but we were one of the first people to look at this, look at gender biases and stereotypes in word embeddings. If you look at embeddings of men and women and computer scientists, you can see these different biases. So that was actually quite impactful research agenda, thinking about not just the algorithms, but also the societal impact of these algorithms, especially with the AI models. And then that carried me over with me as I started at Stanford in 2016 to start my own group, where our focus now is still this dual focus. We do work on developing AI algorithms, large language models, etc., but also looking at these applications of the algorithms in medicine and healthcare.
Got it. And so that makes sense. I mean, actually, let's take a step back. We start every in-person event with an icebreaker, so we can get to know you on a more personal level. So if you could invent any piece of technology or solve any scientific mystery, regardless of current limits, what would it be and why?
It's a good question. So one thing that I really liked when I was little was this comic book. It's this Japanese manga series called about this robot cat. It's like Doraemon. And so he's actually a cat that came from the future, sort of like an AI system, but he will act and talk like humans. And then he have all these sorts of amazing inventions from the future. And the one that I like the most would be actually this bread that you could eat the bread. But the thing is that you can also print anything you want on top of the bread. And if you eat that, then you automatically memorize everything that you print on the bread. So if you want to learn about all the physics formulas, you just print that on top of the bread and you eat it, with peanut butter and jam. And then now you actually have learned and memorized all the physics formula. So I think something like that would be great. It would be a lot of fun.
I think this is a common topic that when people are asked this question comes up, which is this idea of, I think it's particularly intellectually curious people are always trapped by the rate of input of research or work they're able to read or take in. I think maybe that's why Neuralink is so popular, or why people are so excited to work on it, is like constantly trying to figure out this limitation to our human abilities of how much information we can take in.
Yeah, that's true. Although I don't know how much bread I can eat, but that will be another venue of information intake.
Yeah. Great. So now we've kind of gotten to know you. Would love to dive into some insights in AI from your career experiences. So maybe let's just broad overview, like dive into your journey. How has your interdisciplinary background in biomedical data science, computer science, shaped your unique approach to developing reliable and human compatible machine learning that you may see from other colleagues across different disciplines?
Yeah. So it's a good question. I think a lot of it has shaped the kinds of questions that we ask and the kind of research that we do. Right. So one of the most important things about, at least about being an academic, is to figure out like, what are the interesting and important questions to ask. Right? And for us, I mean, there tends to be like two types of questions that I find the most exciting, intellectually exciting. One type would be more about the why questions, like how can really try to understand what is going on, right? So, like, for example, if I look at a big transformer or big language model, can I really try to understand what is going on behind the system, right? Viewing that as like a complex system that we want to study. And then the other kinds of questions that I'm really interested in are the more things that involve, what can we really do to have a societal impact, right? In our case, a lot of that looking at health impact, like what can we really do to improve the health outcomes of large number of individuals, right, of diverse populations, right? And for that part, we've been working a lot more on these translational projects where we, for example, like take an AI algorithm that we've built, for example, for like assessing heart diseases, right, and thinking about how do we really translate that into practice, right? Put it into the clinical workflow so that it's the maximally beneficial and maximally informative for clinicians to make better decisions.
So being a prominent member of the Stanford AI lab, in what ways do you see the convergence of AI and biomedical data science transforming healthcare? And what are some emerging trends or technologies you find particularly promising? I think one of the main out of a lot of voices that at Stanford that are talking on this, I think a great course in generative AI for healthcare at Stanford Medicine is taught by Justin Norden. And it seems that many advances, at least from sitting in on that class, it seems that many advances require sort of collaboration with larger providers such as Epic and Cerner. And wondering how you think about that more broadly for biomedical data science and AI.
Yeah, so I think it's a tremendously exciting space. I think healthcare is one of the areas where AI can and is already having really substantial impacts. Right. So one thing that people may not realize is that even now there's over 200, or there's actually over I think 500 medical AI devices that have already been approved by the FDA. Right. So these are algorithms, right, that have been approved by the FDA so they can be used and deployed in hospitals on patients. Right. So it's actually quite a large number. Now, if you look at what most of these algorithms are doing, so most of them are like computer vision algorithms, right? So things like helping the doctors to segment out different lesions in the tumor, right? Or in the case of something we studied, like looking at videos of people's heartbeats, right, to assess different risks for profiles and do some sort of analysis, right? So I think the current generation of the medical AI algorithms that are being deployed are mostly based on sort of computer vision, sort of image analysis, these kind of deep learning systems. I think we'll start to see a lot more of these more like large language model type applications of AI in medicine and healthcare. I think that that's just starting. That people are exploring different applications of LLMs in everything from like early stage like patient education outreach, all the way to like patient recruitment into clinical trials, right? All the way to like decision making, decision support for clinicians. I think there will be a lot of exciting applications throughout the medical pipeline.
Right. I think healthcare is also a space in which it's not just a software problem. I think there's also kind of the hardware issue. Yeah. I think we've both worked on kind of heart disease, like screening / kind of detection type problems. Mine was at Stanford Medicine. And I think one of the ways we got around we got to solving that problem was through interdisciplinary team, people from Stanford Medicine, people from the electrical engineering department, and also computer science. And I think that's one of the reasons why a background like yours is kind of uniquely suited for solving healthcare and AI, because it is a multifaceted problem where it's not just a data provider problem, right? Such as how do you work with Epic and Cerner? There's also a lot of analysis done on the algorithms, on the hardware level. So I think that's kind of an important thing to keep in mind when working on healthcare.
Yeah, that's a great point. And even though I come from a computer science background, right, but I've been actually very fortunate to have students and postdocs that come from other perspectives, right? So most of our students come from computer science and also some from electrical engineering and statistics. But I also have several MD PhDs who are students or postdocs in my group, right? So it's actually great having them in the group because they see patients every week, right? And then the rest of the time they spend in my group working with our CS students, developing these algorithms. But it's great to have this very direct patient-facing perspective.
Right, right. So we've talked about kind of your work in relation to the Stanford AI lab. Maybe you could elaborate on the vision and mission of Stanford Data4Health Hub, and how, as its faculty director, you're steering it to harness the power of data for healthcare advancements.
Yeah.
And this is a really critical area, given when blockchain was really big, people hoped that a lot of data would be held on the blockchain, so that people could, one, have ownership over their healthcare data, but two, open up data analytics to everyone. Because historically, what we saw over the past 20 years are these kind of, there are people in healthcare that have made a lot of money on aggregating data and solving that really unique and challenging business problem. But curious to hear how you kind of address that issue at Stanford.
Yeah, so I think data is really one of the biggest enablers, but also the biggest bottlenecks for AI, especially for the the recent very large AI models, right? Especially if we're looking at healthcare data, right? There's a lot of challenges due to privacy and security, and because the data is quite sensitive, it's often a lot of constraints on what data can be shared and what data can even be used to train models, right? For example, if you're looking with patients' medical records, and currently you cannot actually even put that into ChatGPT, right? Because of risks and security and privacy concerns. Right? So a lot of what we're trying to do, both as part of the center that I lead at the Data4Health and also in my own research group, is thinking about this, like what we call this data-centric perspective for AI. Right. The idea here is thinking about, like, first, how can we improve the quality of the data that we work with? Right. Oftentimes, especially in healthcare, the data can be very noisy and heterogeneous. Right. A lot of missing data, a lot of misannotations. So a lot of biases in the data that if we train the algorithm on those data, that can then lead to biased responses. Right. So how can we systematically and algorithmically improve the quality and the reliability of the data? So that's a big part of what the center works on, also what my students work on. Another big part of this is what we call like data valuation. So like you mentioned, right, like the data that individuals generate, especially like your medical records, it's very valuable, not just to you, but also to companies that want to train their models on this data. Right. Similarly, like data from New York Times, right, from other news organizations are extremely valuable to large language models like ChatGPT, who wants to have access to that kinds of data.
Right.
And it's a huge debate right now of how should we think about regulating or even potentially compensating, right, for the data generators, which could be individuals like us, right, or writers, artists, people like organizations like New York Times. Right. And a big part of that is thinking about how do we even attribute and understand what is the impact, right, of individual data on the downstream analysis and downstream machine learning models, right? Because that's sort of a necessary ingredient in order to do any kinds of attribution or compensation, right? So that's another big problem that we'll work on, is to figure out, okay, if you have a model that's been trained on some kind of user's data, how do we then link the model's behavior back to the original training data? Right? So we can say that if the model is having this behavior, right, there's having this improvement, then it's really attributed to the benefit of your data, right? And then that's why this you should perhaps get some compensation or get some credit, right, for the value of your data.
Right. And one of the things that you mentioned, kind of getting potentially getting compensation for your data. I mean, this is sort of open discussion across industries. I was at a Stanford Law event with the U.S. Patent Office, I think one of the people speaking was Mark Lamley, of course, at Stanford Law, and one of the things he was talking about was how do we think about compensation for not just in the healthcare data, but in general text data, maybe New York Times data. When a large language model trains on that, who gets compensated? I think on the one hand, you have a lot of people saying it's too big of a problem. It's impossible to solve for, particularly because how do you even measure how influential that data was on the gradients in the model? And then the other side, people are saying, well, using the music industry as a case study, no one thought we could particularly attribute music royalties because how much music there is out in the world when kind of some of these kind of web 1.0 companies came out, but we eventually solved that problem and kind of wrangled that. And it's interesting to see. Sure, people may be sensitive about the text data they generate on Facebook or Instagram or their images, but how sensitive people will be with their medical records, right? And surely if we democratize that data and we also realize we need to compensate people when we incorporate that data into a model, that will probably be some of the most valuable data in the world and could potentially be a source of revenue for people moving forward into the future if we're able to solve that problem.
Absolutely, yeah. So I think this is a really important set of questions. First, because the marketplace of data is actually growing really rapidly, right? Like even now, there are already data markets, so similar to how people can go on like Amazon and buy electronics or buy books. You can also go on Amazon and actually buy data sets now, right? Amazon actually serves as a platform whereby third parties, and there are thousands of data vendors who will go on Amazon and then they can buy and sell data sets. Right. And you can even go on there today and then buy data sets or buy it's like a streaming model. You can get access to like a data stream of all sorts of interesting data, like people's foot traffic to different stores, right, to Home Depots in the US, right? And you can imagine that could be useful for the advertisers, right? And you can buy health-related data. So I think that there's already this rapidly growing data marketplace, right? But it's still just emerging, and I think that a lot of questions around how do we design the marketplace, these mechanism designs, right? How do we design the pricing schemes, and how do we come up with sort of technical ways to then link all of this data and downstream purchases right back to the individual data producers? Right? So I think those are super interesting questions that so we actually taught a class here at Stanford. I did with a couple of colleagues the last few years around these topics.
Right. And so moving on, in terms of striving for statistical rigor in machine learning, that often presents its own challenges. Like, how do you navigate the trade-offs between theoretical robustness and practical applicability, especially in healthcare? So for our screening for heart disease problem, you read some papers on how well they can analyze a heart disease data set using modern computer vision techniques. And when we actually went out and deployed our heart disease screening software and hardware, you now have sort of lower data quality because you have, in our case, a 3D printed stethoscope. And so you're dealing with kind of the real world where there's ambient noise. Data may not be as clean. You have to do that cleaning yourself in the data processing pipeline. But just in general, like, how do you think about the statistical rigor of machine learning, both in kind of theoretical world versus out in the real world?
Yeah, so I think especially in the real world, it's really important and useful to have ways to audit AI systems, systematically audit AI systems to identify what are the major failure modes, right? Now, for example, oftentimes in machine learning papers, people just report the aggregate performance of your algorithm, like maybe like the average AUC, right, or the average F1 score. And maybe you have a very good F1 score, you have a very good AUC in aggregate, right? But that number is a single number that can actually mask a lot of potential failure modes of your algorithm, right? So maybe the algorithm works well in aggregate, but there are specific kinds of devices, different kinds of patients, like you mentioned, where the algorithm would have systematic mistakes, right? Would have biases.
Right.
So a part of the goal of doing these holistic audits is to try to go in and see, can we try to identify what are all the error clusters and error modes of the algorithm, right? And then try to maybe interpret and understand mechanistically, if possible, like what's behind each of the error modes. right? Is it sort of technical errors, like there are imaging differences that leads to that error mode? Or are there more differences in the patient demographics, right? The patient characteristics that leads to those errors, or more like user errors, right? So ideally, what we try to do then is to create auditing frameworks, which are itself like algorithms, right? That can then we can then apply those auditing algorithms like to medical AI devices, right? And then try to understand what are the failure modes and also the mechanistic reasons behind each of the failure modes, which can then inform future improvements.
Mm. I think one of the things that you're kind of diving into is systematically going about the way we measure, the way we think about what the goal is. And I'm curious, what you think about as we've established these new methodologies and ways to take healthcare into application. Looking towards the future, what are some untapped potentials or frontier areas in biomedical data science and AI that you're excited to explore, and how do you envision them contributing to advances in human health and disease understanding? One of the things I think about when I was working as a machine learning engineer on a medical chatbot, we had this humongous database, a knowledge base of different symptoms, different diseases, and how do large language models like OpenAI's models, how much of that is not necessary as much anymore now that we have large language models that can read, that have covered basically almost all of the internet, and what is this role for these kind of data intensive methodologies into our data pipelines? That's something that I think about moving forward. Curious to hear your thoughts.
It's a good question. Certainly, these very general purpose models like ChatGPT have been trained on a huge amount of publicly available corpus, right? So they're very good for these general kinds of conversation things. But I think there's still the room and the need for these more specialist and vertical generative AI or large language models that are trained on these or fine-tuned on the individual domains, right? One reason for this is that, for example, in healthcare and medicine, there are a lot of proprietary data that even OpenAI would not have access to, right? And there are only so much you can learn just by reading the publicly available papers and Wikipedia, right? But if the algorithm can be trained on the patient's medical records and medical images, then that can lead to another layer of much deeper insights and more actionable insights that can help the patients and help the clinicians, right? And that's not something that's currently available with existing ChatGPT, right? Because they're not able to access and being trained on these proprietary medical images and data. So that's one of the things that we're working on, is to develop these more domain-specific language models or multimodal language models, right, that have better understandings of like specific medical areas compared to the general purpose models.
Yeah, I think one of the issues with the private data is that I forgot the exact statistic, but something like 90% or 80% of the world's data is behind a paywall or firewall.
Yeah.
And oftentimes that is the most valuable data and could deliver the largest advances in accuracy and performance and efficiency. Like how does that affect the role of kind of democratizing AI research if a lot of the data is behind these paywalls and firewalls? And is there anything that everyday researchers can do to address these issues?
It is a huge bottleneck, right? The fact that a lot of this data are proprietary. One sort of really fun project we worked on recently was to see, can we actually come up with other creative sources of data, especially like medical healthcare data, right? So just to give you an example, so it turns out that when doctors, when they see sort of ambiguous microscope images, right, what's called pathology images, they actually oftentimes post those images on Twitter, right, and then ask their colleagues from around the world to sort of discuss, like, oh, what do you think is going on in this image, right? And before they post it on Twitter, they make sure often the images are de-identified, right? So they could actually post it without releasing the names and information about the individual patients. But this is actually a really interesting source of data. We actually went through Twitter and we curated basically hundreds of thousands of high-quality Twitter threads. So each Twitter thread now corresponds to when an instance when a doctor will post one or more high-quality pathology or medical images, and then they also have the corresponding dialogue and discussions by multiple experts, right, from around the world about what's going on in that image. So those are basically, essentially, very informative dialogues and conversations by experts, multiple experts around medical images. That's all actually publicly available in the public domain, but people just haven't looked at it before, right? And we showed that you can first curate that data. So that's now one of the largest publicly available such multimodal medical data sets, right, with both images and conversations by experts. And then we've also trained a visual language model, right, on top of that data. So this time it will be a chatbot that can understand both medical images, like pathology images, and also be able to understand expert questions, like natural language questions, right? So it can then help the doctors could actually put in a new image, and the model, then the chatbot will be able to provide some descriptions of this image.
One of the issues, though, so I love the creative take on data aggregation, data generation. Something that we've talked about on this podcast is potentially using open source large language models, becoming very efficient in the way you train them, using creative data pipelines to do your, if you're doing a question answering system, have a more efficient retrieval and text generation process. But then there's also some creative work you can do on the data aggregation, data generation side that you kind of alluded to. Now, I think this is a great thing to do on your own if you are a computer scientist, electrical engineer, or you're statistician. How do you think about the role of subject matter experts, medical professionals, in informing your work and kind of the next steps you'd like to investigate?
Yeah, so I think it is really important to work with the actual clinicians very closely, right? So often in many of our projects, we'll have sort of these two stages. Right? The first stage would be more on the CS side, right, where we actually curate the data that we could get our hands on, and then train the models and do the standard kind of machine learning AI kind of evaluations, right, where you leave out some subset of the data and see how well does the model work on that, right? So things that everybody would do, but then we don't want to stop there, right? So the next stage, oftentimes actually the stage that would take more time would be to do more user studies. And for the user studies, oftentimes we want to recruit some number of experts, usually clinicians in our case, and then have basically each expert often will spend multiple days or multiple sessions, right, with the AI algorithm under some sort of semi-controlled settings where they would use the AI algorithm to solve some of their tasks, but we will try to monitor at like the keystroke level, like exactly what they do and how much time they spend in different parts of the AI algorithm to understand like what is the human AI interaction, right? Because one of the learnings that we've seen is that oftentimes, right, the goal to build this AI, especially in medicine, is not to build the best AI by itself, right? That has the highest the leaderboard scores, right? But we want to have the AI algorithm that's the best at helping humans to make better decisions, right? So AI is still, it's a difference between having the best single player on the team versus having the best teammate, right? We want the AI to be the best teammate because oftentimes, the human doctors are still the ones who are making the final decisions, but the AI will be a valuable assistant, right, to that doctor. And what we've seen is that often the best single AI algorithm, right, that performs the best by itself, it's not necessarily the best teammate, right? The best teammates may not have the best AUC or the best accuracy, right, but they have other characteristics that somehow complements the human clinicians, right, and figure out what makes an algorithm a very good teammate. So that's actually a really important part that's often missing in the AI research, but it's something that we spend a lot of time on, especially in the second stage where we do these user studies.
Wow, I mean that's really interesting, and it reminds me of when we on our heart disease detection team, originally we were planning that how subject matter experts can actually impact the software architecture of your system. So an example of this is that we originally designed the system for the machine learning model to be on sort of inference to happen in a cloud format. Now, what you realize is when in actuality, in deployment, the mobile device that was running the machine learning application may not have internet at times. And so you actually want the model to run on the device at the edge, and so you have to redesign the model to optimize for speed and space efficiency, and then also optimize how you transmit the data. You can't send it out to a cloud system.
Yeah, the systems side is really important, and also the importance, like how does the algorithm communicate, right, with the human users, right? Because we know that even as consumers of data algorithms ourselves, like the way that the algorithm visualizes its results, right, can have significant impact on how we process that information, right? So that's also where we spend a lot of time on developing, thinking, and testing different ways that the algorithm AI communicates its results to humans.
Are there any core principles that you follow there, or is it really more on a case-by-case basis, do you think?
So I guess one of the ways we look at this is that, it's similar to a bit like this reinforcement learning from human feedback, right? So we want to really understand what is sort of the fundamental reward model for humans, right? And if I look at the standard machine learning algorithms, right, most of them are trained with sort of by minimizing square root laws or cost entropy. That's effectively assuming a particular kinds of human user, right? As in particular, it's assuming a kind of a human user who's essentially like perfectly rational, like really understands the probabilities, right? If that's my end user, then minimizing cross entropy or minimizing my standard machine learning objectives makes sense for that ideal user. But we also know that humans have our own cognitive biases, right? For example, we don't understand probability very well, not as well as we like to, right? Most of us are very much influenced by everything from like anchoring effects, right? Like who did we talk to before? Recency biases, like what did we most recently read or watched, right? And also just the difference of our own biases based on our own experiences, right? So part of what we're trying to do then is to see, can we actually come up with reward models that captures the different human cognitive biases and stereotypes, right? So then instead of using the standard machine learning objectives like cross entropy, which assumes a particular idealized human, let's actually put in the more realistic reward models for humans as the training objective for my algorithms. And then we can use that to sort of produce algorithms that are likely to be more compatible, more complementary to the human and users.
I think what you bring up is something that's really interesting, which is this convergence of different fields in machine learning, or maybe you could say machine learning broadly, in that when I was first deciding which area should I specialize in, you had computer vision over here, you had NLP over here, maybe the reinforcement folks that really focus on robotics. That's where really reinforcement learning was shining and running simulations. But then what we end up seeing is that actually the NLP and the computer vision folks might work together. That kind of converges in these deep learning techniques where you could kind of use similar architectures for both visual applications and text applications. And then also reinforcement learning, which I always kind of just associate with robotics and simulation, was also going to influence the other spaces and how they designed applications in real world deployments. Curious to hear about you're a two-time Chan Zuckerberg investigator. Could you delve into the objectives and anticipate outcomes of the products you are leading? Because it's a little bit different from kind of the works that we've talked about thus far.
Yeah, so for the last 7 years, I've been really fortunate to be an investigator in this what's called the Chan Zuckerberg BioHub, right? So it's a part of this organization started by Mark Zuckerberg and his wife Priscilla Chan, who is actually a physician, and then they basically decided to invest most of their resources, right, towards studying and addressing human diseases and improving human health, right? And the BioHub, which is based in San Francisco, is sort of one of the big investments that they made, right, to bring together researchers from the three major Bay Area universities, from Stanford, Berkeley, and UCSF, right, to come together to the BioHub, which has like a physical location in Mission Bay, to really try to tackle what are the most important and impactful problems, right? So, for example, some of the problems that we study as a part of BioHubs to understand, how do the individual cells in the body, right, in our body, how do they change during aging process, right? Because aging is like one of the key drivers of many of human diseases, right? So one of the projects we've done is to study how does the aging affect the individual cells at the molecular level, and then also like what are the effects of things like exercise, right, on aging, right? If you actually exercise, does that actually change the molecular aging clocks of individual cells? Right, so these are the kinds of, I think, quite ambitious like moonshot projects that have been enabled by the BioHub. Right? And there's a ton of great people and great research projects going on in the BioHub. Many of them have similar flavors of bringing together new technologies like single cell analysis, genomics, machine learning, but then to tackle problems that have both fundamental biological insights, but also have this clear translation to human disease and human outcome, right? So that if we understand and make these biological discoveries, this can really change how we think about disease and health.
So when you're trying to solve a problem like this, I mean, what are the key roadblocks to your work there? Maybe you could talk about how you're able to tackle them, or maybe you weren't able to tackle them and you kind of had to go around the roadblock.
Yeah, so with these kinds of projects, often we work very closely with experimental groups because we first need to generate the right kinds of data. And again, it comes back to data. But here, often they're not like patients' medical records, but they're often these kind of involves more advanced biotechnologies to generate these kinds of data, right? So one of the big kinds of data that we use are called like single cell atlases. Right? So the idea here is that we want to basically take all the cells, right, in the human body or in the body of different animals, and then try to sequence and understand like what is the gene expressions or the protein abundances in the individual cells, right? Then map out that cell by cell, and then see how does that change, right, as the individual gets older or as they develop different diseases, right? So that is actually just a tremendous amount of experiments and biotechnologies that needs to be developed to collect that kinds of data. So a lot of our time is working with our collaborators on designing those experiments. And then it also generates, I think, extremely rich and exciting data, right? Longitudinal data, spatial data that we can then develop machine learning algorithms to analyze.
Okay, got it. And we've kind of talked about the key parts of your career from the Stanford AI lab to kind of your work in biomedical data science. Maybe moving first to the past and then to the future, could you reflect on your time as a PhD at Harvard and a Gates Scholar in Cambridge? How have these diverse experiences influenced your research philosophy and the methodology, the way you conduct your research? And really, we're asking this from the perspective of more novice researchers, maybe current PhDs, and how they're creating their style and what questions they're trying to ask throughout their research.
Yeah, thanks. I think that's a good question. So I come from a bit more, I'd say, theoretical background, right? Because a lot of my work before, was more on the mathematical side of machine learning and modeling, and I think that's actually pretty common, right? So usually, especially before the recent wave of the big deep learning models, right? A lot of the kind of more machine learning research is typically a bit more about how do we model these problems carefully, right? Maybe with probabilistic graphical models. Right, or how do we try to understand some of the statistics of the data, right? So these are smaller models compared to what people do now with transformers. But I thought it was actually, especially when I was starting out as a student, it was actually a very useful experience, right? To be able to really have models where I can understand every single part, right? Where I built entire models, I can perturb and update all the different parts of the model, and really write down mathematically, right? What are the properties of those models, right? Even though that's often not tractable to do that with the biggest GPT type models. But I think it was still a very useful kind of training, right, to go through as a student, especially as a very young student, right? Like how do you really understand all the engineering aspects, right, behind and the scientific aspects behind the models. And I worry that maybe some of that might be missing, especially with some of the new generation of students, right? Often the models are more powerful now. You can just ask Copilot or ask ChatGPT to even write reasonable code for us, right? And people can get reasonable results out and write nice papers with large language models without really having to understand all the building blocks, right? I think that's exciting in many ways, and also enables faster iteration. But in some cases, also maybe leads to shortcuts by students where maybe they don't really take the time or have the patience to really understand what the mathematics, right, behind the science behind a lot of the systems they're building. Right. So I think that's one advice I want to still try to give to my students, which is to think deeply about the models that they're building, they're working with, right? So even that may not necessarily be we'll have to prove theorems about every property of these models, right? So that's hard to do with these transformers and deep learning models. But I think there's still a lot of general intuitions, right, that can come from all these deeper understandings that are useful then for the research that we want to do.
So I 100% agree with you on this issue. And I think first, I think a lot of people are being encouraged by Silicon Valley to not worry about the underlying machine learning techniques and instead just use the APIs from OpenAI or any other tools. And the rationale is move fast and break things. Don't worry about it. You know, if you're just a software engineer, you don't need to study machine learning and the past techniques to solve this issue. You can just jump right in and use these tools. And this is something that I'm a bit hesitant against. I mean, I have 3 textbooks that I read at least a few minutes every week, which are Elements of Statistical Learning, pattern recognition, and the third textbook is Machine Learning: A Bayesian Approach. And I think you should never forget those fundamentals, even if most of your work is done using some LM tool. And most of our research at Stanford, DSP, Demonstrate Search Predict project, is mostly abstractions over language models. So we don't have to worry about the underlying machine learning techniques as much. Now, to caveat that, when I was a ML engineer working on a chatbot, the techniques that worked with the highest accuracy and the lowest latency oftentimes were the techniques that come out 10 years ago, 20 years ago. And then marrying that with more recent large language models, and then you have a differing opinions and you merge the result. You do a merger result. But I 100% agree. Do you think that skill will go away in 10 years where people will just kind of create abstractions of their models so much so that that underlying knowledge will disappear? I mean, or maybe there's certain people who it is unnecessary to learn the fundamentals of machine learning, and then there's other people where it still is necessary. Are there any areas where maybe in 10 years it still will be necessary? I'll give you an example. The people who train large language models, like kind of distributed deep learning folks, I think we'll always need to understand the underlying mechanisms, because you have model parallelism, data parallelism. What do you do with the weights? How do you train the weights with diverse data set across systems? How would you pick and choose these areas where that mathematical grounding will still be important?
Yeah, I think, like you said, first we do want to make a distinction about who is the audience, right? There are lots of practitioners, more consumers of these models, right? And for them, maybe it's okay if they don't really understand exactly what are the underlyings of the different transformer layers and optimization methods. But for them, maybe the critical skills they need to understand would be how do they interpret and evaluate, right, the output of these models, right? And make sure that the models are not hallucinating. How do they audit the models, right? How do they track it and monitor it, right? So the skill set for these kind of more consumers and practitioners, right, could be different from the skill sets than a second group, which are the core innovators and developers, right? Like if you're actually trying to do cutting edge research where to improve the inference efficiency of these models or coming up with new architectures, then you still need to really understand what's going on at this core mechanistic level, right? I mean, I do agree that because there are, as these models become more and more mature, especially these kind of large language models, I think we will need to rethink and need to change what kinds of things we emphasize and teach in data science and in computer science, right? And in some ways, right, especially for most of our students who are going to become more consumers of these models, right, like maybe the more important skills would be more about how do they interpret, right, these models, or how do they responsibly use these models, and less about memorizing the specific Python syntax, right? Because now they can get that syntax with assistance from Copilot, from ChatGPT pretty easily, right? They don't need to memorize all of the packages they need to do, right? But it's it's still critical for them to be able to look at an output, maybe that's produced by a large language model, and be able to critically ask questions and figure out like what are the, does this make sense? Right? Does this track with their intuition? How can they quickly look at these output of language model to know whether they're hallucinating? Right. I think that it's a different set of skills, but we do need to evolve how we teach these skill sets and teach our data science curriculum.
Right. And a good example of this would be in Excel, there still is a linear regression function. You don't need to know how linear regression works, but you do need to, at least most business users who use Excel for the linear regression function, they know how to interpret that and present that to their boss, and they don't need to know what's going on underneath the hood. Moving to your work at Microsoft Research, a different institution from Stanford, curious to hear about the key learnings and experiences that you had there, how they inform your current work and current research focus, and have you had to change the areas that you focus on as you move to Stanford?
Yeah. First, I really did enjoy my time at Microsoft. And I think it's definitely a really exciting place where we're doing a lot of very creative, interesting research. And the main reason why I always knew that I wanted to come back to universities, or to a setting like Stanford, is that at universities like Stanford's, you still have much more flexibilities to do open-ended basic research, right? I think that's especially the case now, where there's I think somewhat increasing pressure, especially in industries, right, in this arms race about large language models, to focus more on the products and maybe not publish as much as before, right? But I think that's still, we have some unique advantages in academia where we can sort of stand a little bit outside of that arms race of these companies and be more of objective, provide more objective assessments, right, about what's going on in these different models, and do these things like we do for auditing. And I mean, the second big difference is that the ability to really work with quite interdisciplinary teams, especially students from different backgrounds. Like if you're, for example, working at a company like Microsoft or Google, or it's I mean, you're working with a lot of talented people, but they're mostly coming from like engineering, computer science backgrounds, right? You could try to get collaborators who are MDs, but it's going to be harder, right? Whereas here in my group at Stanford, I actually have several MDs who are like full-time members in my group, right? And that's a huge difference, because then we can work together every day on these problems, and we can work on more ambitious, longer-term projects, right? Like that will take 3 to 5 years to do, right? Which is often like a bit longer than the horizon of many of the products you do at large companies.
Yeah, and I think also what you'll see is that, at least what I've seen, is that in a place like Stanford, it's incredible to see so many MDs who have experience working with engineers and are curious about technical concepts. So they'll, at least know it at a high level and be able to communicate with you a little bit more. Whereas if you move into a more enterprise area, more commercial or startup, the MDs that you may be working with may not have a history of working in the space, and really are just more curious about working together with engineers, and are kind of coming up the learning curve, which can be a little more difficult to communicate in a cross-disciplinary team than if you had an MD who's been at Stanford for a number of years, is very experienced working with the computer science department. So definitely some pros and cons to both experiences. So great. So last question, closing question. What is the AI industry going to look like in 1 year? And why is this important to ask is because this helps people think about, if they're a startup founder, what to build, if they're a researcher, what questions they should be incorporating into their research. So yes, although we know that you may not have a definitive glass to look into, what are your thoughts on the future?
Yeah, so I think in the next 12 months, we'll continue to see just really rapid and exciting developments in the generative AI large language model space, right? Like, many of these models that we work with, like ChatGPT, have been invented, came online like less than a year ago, right? So they're still in the early stage, and we'll see, I think, and a lot of companies are really struggling with like, how do you think about their large language model strategies, right? How do we really integrate that into workflows? And there are very cool demos that people can build, but how do you really do that integration? So I think that will be a big focus in the next 12 months, is really, as these models become more mature, right? How do we really integrate that into each of these vertical industries like healthcare, finance, right, consumer, and that creates a host of new opportunities, right, for startups and and researchers.
Got it. All right. Thank you so much for joining us, James. And thank you, everyone, for listening. Collective Nation, as we wrap up another episode of the podcast, I want to express my gratitude to our guests and to you, our curious and passionate listeners. Today's discussion has once again illuminated the terrain of AI, offering us a rare glimpse into the minds shaping the field. As always, we're building this podcast and Gen AI Collective community, so please reach out with any feedback or suggestions. If you'd like to be a guest on the Collective Intelligence podcast, please get in touch with us. Details for doing so will be in the show notes below. And if you enjoyed this episode and would like to support the Collective Intelligence Community podcast, please leave a review or a comment on your favorite podcast platform. Thank you for being a part of this journey. And until next time, keep exploring, keep questioning.